Okay, thank you. Hello, everybody. Thanks for joining. So today's session will talk about the QoS feature on Spitfire, and it's a pretty lengthy topic and number of slides actually. So most likely we'll have a couple of sessions on this. So we'll start today and see how much we can cover, and then probably next week we'll continue the same topic. And feel free to ask questions. There is some similarity between Spitfire QoS and other platforms like NCS 5500, but there are a lot of differences in behavior as well. So we'll start from the pretty basic architecture of the VOQ, and then we'll build on the discussion. But feel free to ask me any question anytime, and we'll try to make it more Q&A whenever you guys have any questions. So we are packed with the agenda. We'll start with the easier part of it, that what's supported and what is not supported. We'll look at the policy configuration model, VOQ architecture, even though the VOQ architecture is not new to the Spitfire platform, but in order to understand the QoS, and especially when it comes to the CLI part of it, we really need to understand the VOQ architecture, so we'll have just a quick revision on that. We'll talk about the Spitfire queuing rules, and then very important part of the discussion is SMS and HBM architecture. Then we'll talk about the queuing and the congestion management, classification, marking, and policing. And at the end, we'll talk about the bundle QoS if time permits, if we get to there, whenever we get there. So to start with what is supported and what's not supported at a high level, the following features are supported, which are policing, marking, queuing, shaping, and congestion management. Just keep in mind that we have only ingress queuing. There is no egress queuing. There is no queuing on the egress side. All the queuing features or all the features which require the queuing is only on the ingress side. And we'll talk a great detail about that. The maximum classes supported per policy is 8 to start with, but recently, based on one of the customer's requirements, this might have changed in a certain release. If I'm not mistaken, it might be 7 or 12, but make sure you can check that. So it might have gone to 32 classes per policy. And the maximum match statement per class is 8. And by the way, that change in the number of the classes per policy is on the ingress side. On the egress side, it is still 8, or it should still be 8. Some of the unsupported features, which we don't support, and we'll talk about that in great detail as well. 3-color or color-aware policers like 2-rate 3-color, that's not supported. Hierarchical policers are not supported. There's no support for the L2 ingress classification, and one of the very surprising and probably the important part is WRED is not supported. We do have a workaround for that, and we'll talk about that again in great detail, but the basic feature of WRED is not supported because of the hardware limitation. And again, we'll talk in detail about that as well. So how the packets have schedules on the Spitfire? So packets are queued on the ingress side, where we have the VOQs, and then we have an output scheduler for each interface and each sub-interface. And again, this is the high level. We are just touching upon some of the topic, and we'll go into a lot more great detail actually. So it's not just the bullet point. These are just the some of the topics. We have to spend some time on that. So the queuing is on the ingress. There is an output scheduler for each interface, which generates the credit based on the rate of that particular interface, and then it distributes those credits to the ingress traffic manager block. And these credits distribution happens based on the priority and the bandwidth configuration. It means that what is configured within the policy, based on that policy, or what we configure, these credits from the egress credit scheduler are being distributed towards the VOQ. Then we have 3 policy config models. Like we have first one is ingress policy. What we can do on the ingress side, we can do policing, we can do marking, we can set the QoS group based on the classifier. What are those classifiers? That can be based on ACL or can be based on DSCP, precedence value, or EXP. And We can do the policing based on those classifiers as well. What we can set on the ingress side, we can set the traffic class, we can set the QoS group, and we can set the discard class. So all these marking actually on the ingress side are for a particular scenario. For example, take the traffic class. So traffic class actually controls the queuing behavior on the egress side or on the transmit side. If we set the QoS group on the ingress side, that actually controls or drives the marking behavior on the transmit side, and the discard class drives the transmit behavior, discard behavior on the transmit side. So whatever we set on the ingress side, based on that, we have to design our QoS policy. And there are, of course, certain limitations, and we'll talk about that. But at a high level, if we need the queuing on the egress side, we set the traffic class on the ingress side and then match on that traffic class and do the shaping or bandwidth remaining ratio or priority queue, for example. On the egress queuing policy, we match only on the traffic class. So if we are doing any action on the egress side or we are applying a policy with a shape, for example, statement on the egress side, we have to match on the traffic class. So we cannot change what class the packet is. For example, we have traffic class 0 to traffic class 7. So traffic class 7 is the priority class, and traffic class 0. We'll talk about that in more detail, but I'm just giving an example that the traffic class 0 is a default class. We cannot change the default class of traffic class 0, match it on a traffic class 1 or the BOQ1, for example. So based on that policy, what we describe within the policy, we select that which VOQ the packet uses. Based on that configuration on the egress side, we determine the traffic manager scheduler rate, that at what rate the credit scheduler will send the credits based on the weight. Weight means that when we configure the bandwidth remaining ratio, we'll talk about that. But based on that, it distributes the credit from the credit scheduler. And of course, based on the priority as well. There is no WRED, as I mentioned, but there is a kind of workaround for that. There is a dual queue limit available, which is based on the match discard class. On the egress side, we can do the marking as well. And in order to do the marking, as we discussed in the previous slide, we need to match on the QoS group. And only we can match on the QoS group if we are doing a marking. So for example, if you take a traffic class, match on a traffic class and try to do the marking on the egress side, that will fail. And when we do the marking, actually that does not drive or impact the queuing behavior based on our configuration, but we are just doing a marking on the egress side. Was there any question? All right. So
one
part. For the
oh, guys.
part,
sorry, go ahead.
Okay, for the scale part, we have this VOQ architecture which imposes the scale limit system-wide. And the reason is, and we'll talk in great detail about the whole architecture, but all these VOQs, they have to be live or they have to live on all traffic managers. It means that if you have an egress interface, for that particular egress interface, 8 VOQs or 4 VOQs, depending upon our configuration again, but by default, 8 VOQs have to be have to live on all ingress slices. So if you have a distributed system with X number of line cards and one interface, any interface could be an egress interface at a given time based on the traffic direction. So that egress interface will have the VOQs, 8 VOQs on all the ingress slices, and any slice can be ingress slice again based on the traffic direction. So these queues are allocated to the interface group. If we talk about the Spitfire architecture, that's not our topic today, but we have slices, and within slices we have the interface groups. So if we take the example of FC48, for example, where we have 2 NPUs, so each NPU has 24 interfaces, and within NPU we have slices, and within slices we have the interface groups, 2 interface groups per slice. And these VOQs are allocated statically at the boot time, means that we cannot have more than 8 VOQs We cannot configure such, but these are statically generated or allocated at the boot time. The max number of the NPUs in the system actually dictate the number of the total VOQs at a particular time. And sub-interface scale ranges from 10 to 500 sub-interfaces per interface group. And in today's discussion, most of the time we'll be talking about the main interface, not about the sub-interfaces, but a lot of similarities exist between what we will discuss about the main interface with the sub-interfaces as well. So first of all, why VOQ architecture? Let's try to go through this slide real quickly because I'm sure that the VOQ architecture is not something new. So in a legacy environment, if you have an ingress port IP1 or ingress port 1, sending the traffic to ingress port 2 and 3, and there is a congestion on egress port 2, actually it would send the message to the ingress port 1 to slow down either or send the back pressure, and ingress port 1 based on that will start dropping the packet regardless of the packets are destined for egress port 2 and 3. That's pretty straightforward. But when it comes to the VOQ architecture, if we have an ingress port 1, we maintain the separate VOQs for each egress port, like we mentioned earlier. So if we have the congestion on the egress port 2, only the VOQ will be notified on the ingress side for that particular egress port, and there will be, based on, again, configuration, our QoS configuration, either packet will be dropped or produced or action will be taken. But only the traffic will be impacted for the egress port 2. So again, we'll go in the detail of the VOQ architecture. So this is at a high level. This is kind of packet flow we look into when we talk about the VOQ architecture. So we have an ingress interface, and then we have the VOQ. This is a kind of slice view or the line card view, we can say. So the packet comes from the interface, goes to a VOQ, and then there is an ingress side scheduler, and then there is an egress side scheduler. So ingress side scheduler requests the credit from the egress side scheduler, and based on the situation of the system and the, again, the configuration of the egress QoS, it provides the credit, and once the credits are received by the ingress scheduler, the packets are being sent over the fabric and to the egress port, and then after the egress port, it goes down to the egress interface. There is no buffering on the egress side, so all the buffering happens on the ingress side. And as we mentioned earlier, that the queuing behavior or queuing is happening on the ingress side since we have the VOQs on the ingress side. So this is kind of more details where picture here where we have three, for example, we have 3 VOQs here, and once credits are assigned based on the policy, a queue will be selected that which queue need to be served. So let's say if we have a priority queue need to be drained out first, and then other than normal priority queues, or we call them PN or NP, those will be, credit will be distributed to those normal priority queues equally, or it can be based on the weight as well. And again, we'll talk about that. If we have a different weight, how that works out. So this is the chassis view of the whole VOQ architecture, where you have 2 ingress line cards, LC0 and LC1, and you have an egress line card, LC7. And on the egress line card, we have an egress interface 100 gig 0700. Now, in order to send a packet to the egress interface, and by the way, again, any interface can be incoming interface for this particular egress interface. So it means that these VOQs for 0700 Q0 to Q7 or VOQs 0 to VOQ7 will be replicated on all ingress slices. So in order to make it a simplified version of it, we just assume that there is only 1 slice per line card. So as we can see that on line card 0, the VOQs are replicated on line card 1 and even on line card 7 as well. So because the incoming interface can be on the same line card. VSC is the VOQ scheduler connector or view-queue scheduler connector. This actually connects the scheduler on the egress side to each VOQ. And VSC is unique for each VOQ. We'll talk about that. We have some of the show commands as well to show that what is the value of VSC. But one thing to note that there are, of course, there are 8 sets of VOQs for each egress interface, but these VOQs have an ID associated with it, or VOQ ID we call it. So if we run some of the show commands, again, we'll come to that part actually. Let's take the example of the 0700 VOQ0. So VOQ0 will have a certain ID, let's say ID 1000. So for a particular egress interface, this is an important point. So for a particular egress interface, in our case 0700, a particular VOQ ID, which is in our case, we are taking example of VOQ0, which is, let's say, 1000 ID, that will be constant for each slice on all the line cards. Means that VOQ0 for 0700 will be 1000 here, 1000 here ID, and 1000 here. Now, how it will be differentiated that from which slice, incoming slice, the traffic is coming in. That's where the VSC comes into picture. We'll run through some show commands. We'll see how that differentiate, but keep in mind that don't be surprised when you run the show command for an egress interface for a multiple line cards or multiple NPUs, and you see still the same QID, VOQ ID. That is the expected behavior. That's by design. So why we have the 8 default VOQs per port? Because we have the hardware which has the 8 output queues per port. And after the 8 default VOQs are created and replicated on all the ingress slices, the VOQ do not need to be deleted as long as the ingress slice exit and the egress port exists. So once you have the egress port, once you have the ingress line card, those VOQs will always be there. Unless, of course, you remove the line card or egress interface is now there or egress line card is not there. When user apply an egress queuing QoS policy or delete the policy or modify the policy, there is no need to delete the ingress VOQs. It means that if you are having a policy with the shape action, for example, so you are not actually creating a new queue. In the older platforms where we have the software queues, when you have these actions associated with the QoS policy, those software queues are generated. But in case of VOQ, those queues are already there. You modify, delete, or add the policy. That will not delete the ingress VOQs or update the system. Just need to modify the egress credit and the transmit scheduler and the VOQ congestion management parameters. And we'll see some of the show command for that. The connection between the VOQs and the VSC, that is stay intact. And there are always, we always use 8 VOQs for the main interface or the sub interface. We can have 4 VOQ mode as well. We'll talk about that. But by default, it's 8 VOQs per egress interface. So when we talk about the 4 VOQ mode, we can have that. We have to configure that with the hardware module profile QoS command. And once we configure that, what we'll have is, first of all, we have to reload the chassis in order to take that effect. And then we'll have only 4 VOQs per egress interface. Now, what it gives us, the rest of the commands will be same. Just the output will show you 4 4 VOQs. But what it gives you the more scale. So you just double everything when it comes down to the scale. The number of policies, for example, ACL. So which queues will be used? Let's say you have a traffic class from 0 to 7. So in a 4 VOQ mode operation, from Q0 to 4, that will become the normal queue or default queues. We call Q0 as well. And then you have 5, 6, and 7. Keep in mind that 6 and 7, they are the priority queues, and you cannot change that. Means that you cannot put the non-priority queue into the traffic class 7. That's by default the priority queue 1 and priority queue 2. So now we'll talk about the queuing overview, how it works out in more detail than what we talked earlier, and some of the probably we might have questions will be answered based on the credit, how the credit request comes in and credit scheduler works out, and what is VSC and how that works out. So for a given So in our case, actually, we have an egress slice 0, and then we have multiple ingress slices. Slice 0, slice 1 could be same line card, could be different line card, but it just a matter is different slices actually. So as we know, each slice has 2 interface groups, and we just focus on one interface group 0. So as we see that interface group actually shares some resources. What are those resources? Credit scheduler. So credit scheduler is not per NP or per slice. Actually, it's per interface group. That's one thing. Then you have output queue scheduling element, and within that you have credit scheduler, which works in the round robin fashion. Then you have transmit the traffic manager port on the transmit side, which schedules the transmission out of these output queues, and these are the output queues right here. Now what we have here, so we are focused on a given interface or given output queue, for example this one on the egress side, and correspondingly we have VOQs on the ingress side. So as we see that we have VOQI, let's say VOQ0, like we talked earlier. Just take first VOQ on each slice. So this output, this particular output interface, for that output interface, we have an output queue, and for that output queue, we have VOQ0 on all the incoming slices. And as I mentioned earlier, this will be the same VOQ number is used on all the slices. So we took the example of 1000. So this will be 1000 VOQ ID, 1000 VOQ ID, and 1000 VOQ ID. Now, how this scheduler knows that, or this output queue will know that from where the traffic coming in, because the ID is same. That comes down to VSC. So VSC and VOQ, that combination will be unique. So VSC for VOQ on slice 1, that will be different than the VSC for the VOQI on the slice 1 versus slice 2 and so on. So your VSC will be unique, and that will differentiate that from which slice the traffic is coming in. So that's one part. So like I mentioned, the same VOQ number from a different slice is connected to the different VSC. VSC is attached to a round robin scheduler in the output queue scheduling element, and this provides a fairness across all the ingress slices. So it means that it's sent in the default scenario when there is no priority and every queue has a similar weight, same weight or same level of priority, let's call it that way. There will be round robin fashion. If all these queues have the packets for this output interface, 1 credit at a time will be distributed to each queue. So 1 credit goes to this, the other second credit goes to this queue, and the third credit goes to this, and then round robin fashion it comes down to that. Unless you have a different way.
How many priorities do we have there? So sorry, how many priorities
do we
have there?
Okay.
Because
so,
I saw only 3 priorities for the previous time.
Okay, so we'll talk about that, the priority levels, but we have P1 and P2, and that's the default priority for traffic class 7 and traffic class 6, or VOQ7 and VOQ6, and then we have the normal priority for rest of the classes, but you can configure from P1 to P7. So you can actually configure all the classes from VOQ7 to VOQ1 with the priority level. And again, we'll talk about that, but by default, you have P1 and P2. That answers the question. So this gray line shows a flow of the packet, and before that, the flow of the credit. So request comes in, request is granted, and then the packet flows comes into that picture. So VSC is the key takeaway from this slice, and VSC is unique for each ingress slice. So each VOQ requires n number of VSCs, and n is equal to the total number of the network slices or the input slices in the whole system. So depending upon how many line cards we have, the n number of VSCs will be required for each egress interface. This is again at a high level. We have a little bigger view over here. So one important part actually we have, again, this is not the discussion about the packet flow in the system, but rather just to give an example that there is an RxPP receive packet processor before we hit the VOQ, and any ingress QoS classification or marking is happening on the RxPP. And once we have classified or marked the traffic, then it goes to the VOQ. What happens within the VOQ? We do the queue limit. We can, if we configure the queue limit, that happens within the queue VOQ. And then, of course, the regular credit request credit grant comes in, and then traffic start being transmitted on the egress side. And again, the same example we use here for one particular output queue. It's the round robin fashion. One credit goes to VOQ on slice 0 and slice 1 and slice 2 and so on. So some of
yes, one question. Sorry to interrupt you. Does VSC would be unique to each slice or each VOQ? Because each slice has
each
8
slice.
VOQs. Okay.
Yep, each slice. Because you have a combination of VOQ and VSC, right? That combination will become unique per slice.
Okay, thanks.
One you have VSC, and then you because within the slice you will have VOQ 0, VOQ 1, and those VOQ 0, VOQ 1 IDs will be different. Let's say 1000, then 1001, 1002, and so on, right? And then again for the next slice, it will start again from 1000 of VOQ ID for the same egress port, but the VSC will be different. So VSC and VOQ combination will tell you that it is a VOQ on slice 0 versus slice 1.
One more question, please. So on the ingress ports, all ingress ports on the same slice will share the same VOQs for sending the traffic to the same egress port, correct?
So we'll talk about that once we go to the architecture, but the VOQs are per slice. Yes, that's right.
Got it. Thanks.
Okay, so if you configure the queue limit, that happens with when the packet is within the VOQ. And then if we have an egress queuing policy, which means that either we are doing the shaping or bandwidth remaining ratio or the priority, that happens on the egress side. And if we have any egress classification or egress marking, that comes into picture when the packet is in TXPP or any egress ACL. If we configure that, that comes into or take effect in TXPP. So this diagram actually tells you that what happens where. The marking on the ingress side and the classification happens before VOQ. So keep in mind this might be important at some point, actually, if we are troubleshooting or some issue where marking is not correctly happening. It has nothing to do with the VOQ. But of course, if there's a queue limit which is not programmed according to our configuration, that's VOQ. And then on the egress side, the classification and marking is happening in the TXPP along with the egress ACL. So how the credit flow? We already kind of touched upon that, but on the output queue scheduling element, that is sends or generates the credits as via VSC. It goes to the VOQ. And credit scheduler decides which packet can be allowed from which VOQ. Again, that is based on your configuration. If we'll take a couple of examples on that, what we configure, if we configure the P1, P2 along with the rest of the normal priority without changing any weight versus we have P1 and P2 and then rest of the classes have different weights. So how that works out, we'll talk about that with the show commands as well, if time permits today, otherwise in the next session. But this will be very clear from some of the show commands. How the packet flows, of course, it's the opposite direction. VOQ receives the credit, sends it to the output queue, and that goes to the transmit packet switching element and then TXPP. So TPSC, Traffic Manager Port Scheduler, what it does, it puts the packet from the output queue to the wire. So it's kind of buffer between the output queue switching element and the TPSC. So there is a buffer there, but like we mentioned that there is no queuing on the egress side. So queuing, when we talk about the QoS behavior, this is kind of, let's say, hardware buffer, right? So before you send out the packet to the wire, so this buffering has nothing to do with the queuing behavior of the QoS, just FYI. So packet received by the RxPP, the microcode process the packets, and then within the round robin fashion, the VSC from slice 0 to 6 on the output queue X. We took the example of output queue 0, talking with the VOQ 0 to VOQ 7 in the round robin fashion. But again, there is a scheduler per interface group, and that scheduler works with the VOQ I along with all the incoming slices. So hardware programs the 8 output queues, output queue 0 to output queue 7, and 8 VOQs on each slice using the VSC. On main interface, there is one-to-one mapping. And why it's mentioned main interface? Because on the sub interface, of course, you will not have one-on-one interface, one-to-one mapping in that case. But in case of our main interface, you have only 8 view queues. But once you start configuring the sub interface, that will change some of the scenarios. And again, in today's discussion, we'll try to understand mostly on the main interface part. There was a question.
Yes. Question here, please. Round robin at VSC slice 0 to 6, or so in case of 6 slices, and in the VOQ architecture, 3 would be network and 3 would be fabric, right?
Yes. Yep.
So,
yes, that's true.
So do you mean 3 slices, 0 to 6, or 0 to 0, 1, and 2? That only network facing slices.
So practically, it will be 0 to 3 because the incoming interfaces are connected to 3, 0 to 2. I mean. Because incoming interfaces are connected to these slices only, and that's where it comes down to 0 to 3. But I think I have to check back based on the slides that is it the fabric queues are involved there as well, but I doubt that because there are no interfaces connected to or physical incoming ports connected to those queues. Those slices, and there will be no request for the credits because there is no incoming traffic.
Exactly.
So and one more question might be the correction here.
And one more question in this similar category is, how about the traffic flow to and from basically from the CPU, the punt path? If you are going to cover that, we can defer it.
No, that's not topics today. Actually, punt path is not included in today's discussion.
No problem. Thank you.
So one more reason that we have the 8 VOQs is the traffic class is a 3-bit value in the packet, and there are 8 combinations possible, and that's why Spitfire has the limitation for 8 output queues. So number of the VOQs used depending upon the policy configured by user. If we have 4 classes, we'll be using 4 VOQs, but rest of the VOQs will be there actually, and they will be counted towards the resources being there but not used. So output queue X, again, will have the VOQ X replicated on all the slices. We saw that in the previous slide, 1 VSC per slice. Like we mentioned that 1 VSC for, this is a VSC for this particular slice, and then we have another VSC for another slice and so on. So in case of previous platforms, for example, CRS, right, they have the separate ingress and egress queues, and that's why there was possibility of thousands of queues possible. In case of VOQ, if we see that, if we have a particular egress interface and depending upon, again, how many line cards are there and which line card is there, we have to replicate all those VOQs for one particular egress interface to all incoming slices, and that's where the scale limitation comes into picture as well. So again, queue selection is done at the egress side using the credit scheduler. Once it decided and informs to VOQ at the ingress side, it is start transmission. There is no buffering again at the egress side, so there is no drop, and that's where there is no policing supported on the egress side as well, right? And again, we'll talk about that once we talk once we go on the policing section. So once we have the credit grant happen, we just send out whatever is received, and hence the queuing happen only on the ingress side. If we have the sub-interfaces, let's say if we have 200 sub-interfaces created on one main interface, every sub-interface will have 8 VOQs, but all compete for the same output queue that belong to the main interface. So in a Spitfire distributed architecture, one egress port takes lot of VSCs, because it is on all the slices, all the NPs on all the LC ports, compared to the fixed platform, because in the fixed platform you have the less number of slices, and this is one of the difference between the fixed versus distributed.
One more question, Imtiaz. In the Spitfire D, I'm assuming that you can have combination of line card types, a line card with one NPU versus a line card with multiple NPUs in different chassis. In that scenario?
No, it says that, no, it talk about the number of the VSCs, right? In a fixed platform, it's fixed. In a case of distributed, it's depending upon how many line cards we have, how many NPUs we have, and how many slices we have. So it just takes a lot of VSCs on the egress side, and that's where the difference.
I was building on that question. So VSC, I believe, is a hardware function, and every hardware, every NPU would have a fixed number of VSCs, correct? It's not a settable function.
Yeah, it's not settable function.
Right. So in a multi-line card, the distributed chassis, if you have one line card with a specific with a single NPU, and if the rest of the line cards have two NPUs, how would you configure that? Because that line card would have peering with a lot of VOQs on all the other ingress slices on all the different line cards, right? Does that limit this sizing at all?
You don't configure. Yeah, you don't configure that. What this bullet point is mentioning, that the difference of the number of the VSCs between the fixed versus the distributed is given fact that these VSCs, again, based on how many line cards we have, how many slices we have on those, they are fixed again, but they are a lot as compared to the fixed platform. So you don't configure these VOQs because they are there. For example, let's take one quick example here, right? You have two line cards in the system. So based on that, actually each egress interface will have certain number of VOQs on each incoming slices. Now you add an additional line card. Now what happened? Are you creating those VOQs actually for the older two cards which were already there? No, actually those VOQs are already there, but it's not activated. Let's put it that way, right? Once you insert the third card, you are introducing more variables, means you are introducing more egress ports. So for those egress ports, the VOQs will already be there on line card 1 and 2. Now you introduce line card 3. You don't have to reload the line card 1 and 2. So means that these VOQs, these VSCs are already there. It's just based on the egress interface, they got activated. If you remove those egress interfaces, it doesn't mean that you are removing the VOQs on the ingress line cards, which are line card 1 and 2 in our case. But they are there. They are just, so once we run some of the commands, actually, we'll come to that part because there are those show commands where you have to define two variables, for example. One variable is the egress interface, and the other variable is the ingress line card. So those show commands take these two variables and provides you the information about the VOQ for an egress interface. So once you do not have those egress interface, you cannot even run those commands, meaning that you cannot even see those VOQs. It doesn't mean they don't exist. That's on the hardware. They are just not activated or initiated, let's put it that way, based on the non-availability of a particular egress interface.
Got it. My question was a little bit different, but this was definitely a helpful conversation. I'll ask you separate on offline.
Sure. All right, cool. Thank you. So on the egress marking and egress ACL, that happens, as we mentioned, after the queuing action at the TXPP. So there is a fairness between the classes in the same policy. Traffic from the multiple ports belong to the same slice, actually, use the same set of VOQs. So WFQ is not guaranteed. It all depends on how the traffic is sent from the TGN. So in case we have one demo slides, or a few demo slides, actually, we'll look into those show commands and we'll explain more over there. So VOQ stats are displayed per device, means that per slice, and how we can create those congestions. Let's take the example again, coming back to this particular point where we are sending the traffic on multiple interfaces, and we have one egress interface. So if you have 200 gig incoming interface and one egress 100 gig interface, now what happens? So this is a congestion scenario, right? So congestion, how we can create congestion? Either we can send multiple ingress interfaces to the same egress interface, or we can have a shaping configured on the egress side, which will create the congestion scenario. And why we are talking about that? There are very important discussion upcoming, actually, where we will see the traffic with the congestion and without the congestion and see how that actually make some difference. So coming to part of the what is supported and at what direction. So kind of pretty self-explanatory slide. Just trying to highlight here that the minimum bandwidth is not supported, and the WRED is not supported. Now we already talked about WRED. Now what that means, you cannot guarantee a certain bandwidth for an interface, which is the bandwidth keyword, right, in our older platforms or previous platforms than Spitfire. So means that you cannot have the bandwidth remaining % or bandwidth keyword that's not supported. What is supported is bandwidth remaining ratio, and that is slightly different than what we have been used to so far, and we'll talk about that in detail again. but rest of like the priority is supported on the egress, queue limit is supported on the egress, and dual queue limit, which is the compensation for WRED, and then early fast detect, these are on the egress side, and on policing is only on the ingress side. As we talked a couple of slides earlier, that why policing is not supported on the egress side, because there is no drop on the egress side, all the drop, because the traffic sent from the VOQ based on the credit grant. Once you have the credit grant, it means that the output queue is available to transmit the packet. There is no point of dropping on the egress side. So there's no drop on the egress side. So policing is not supported on the egress.
Hey, quick question, Mom. Can we do ACL, PBR, all of that on the egress side?
We do ACL, yes. ACL-based classification on the ingress, if that's the question.
Do we do ABF and PBR as well?
See, ABF is the forwarding thing, right? I mean, we're talking about the QoS on the interfaces. ABS is you are impacting the forwarding. So that is not today's topic, but
okay.
I hope Aman or somebody is here who can answer this question, but it should be supported. Okay, so we talked about the why policing is not supported. A drop happens on the ingress side. So the classification, marking, and policing via ACL can be done on the ingress side. We covered that earlier. Queue limit or WRED, that's on the ingress side as well. Bandwidth remaining ratio, it is, we'll talk about that in detail, and then the minimum bandwidth, that's not supported. The reason is we have the credit request and credit grant system, and if we have the minimum bandwidth, it means that we are guaranteeing some bandwidth that will collide with the priority queue, and then the problems will happen. So a minimum bandwidth guaranteed is not supported, rather we have the bandwidth remaining ratio. So some of the rules on the egress side, both queuing and marking policing can be applied together within the same policy or the different policies. But if we apply both, first the queuing get into action and then the marking will happen. Keep in mind that the queuing will happen first and then the marking action will be taken place. Class default always matches on the traffic class 0. We cannot change that fact. So on a class default, you match on the traffic class 0. If you match on the traffic class 0 and try to put it the priority class on that, it won't work. A traffic class without a matching criteria or without a matching class will be sent to the default class. I think that's pretty straightforward, no-brainer there. Only certain actions which are priority shaped bandwidth or remaining bandwidth remaining ratio, queue limit or RED, they are supported in the queuing policy. Again, there's nothing new here. So if all the priority levels are configured, and that's where the question comes comes back actually, how many priority level we have. So we, let's say we can configure from P1 to P7, right? So if we configure all the priority levels, keep in mind that they have to be contiguous. Means that you configure P1, P2, and P4, not going to happen. You are skipping P3, so that's not allowed. If you have to configure 3 priority levels, it has to be P1, P2, P3, cannot be P1, P2, and P7. So at each priority level, when configured, must be configured to the class that matches to the corresponding traffic class. For example, traffic class 7 has to be in P1, traffic class 6 has to be in P2, and so on, right? Like I mentioned, traffic class 0, you cannot put the priority in that goes to the default class. And correspondingly, every traffic class has to go in that particular priority level if we are configuring more than 2 priority levels. So generally speaking, we recommend user to configure P1 and P2, and then the normal priority or priority normal, however you read that, but these are the normal priority classes in the queuing policy in order to protect the injected network control packet, because those control packets might be impacted based on, again, what configuration we have. For the egress classification, we match on the QoS group. We talked about that in the beginning as well. So we have match QoS group 0 cannot be configured. That's the default in the egress policy that maps to the QoS group 0. So we cannot configure that QoS group 0 once we are doing the egress classification. Again, what actions are supported, what's not supported based on the VOQ model versus 4 VOQ model. And again, pretty self-explanatory. priority is not supported on the parent level, but rather is supported on the child level. But what classes are supported only at the parent level? The default class is supported, and then shape is supported at the parent level. Bandwidth we talked about is not supported on at all. But bandwidth remaining ratio is not supported on the parent level, and so on. Right? You have to configure that on the child level. So now we'll go through the HBM and SMS part of the discussion. This is very important to understand because that's where your congestion versus non-congestion scenario comes into picture, right? So what is SMS and what is HBM? These are the memories. As SMS is the internal memory, and HBM is external memory, you can call it. Shared memory system, SMS, and high bandwidth memory. So what it does. So we have the specific ASIC, we have SMS, and then we have HBM. In case if we have no congestion, the traffic comes in, and VOQs are in SMS, and traffic goes to the VOQ, and whatever actions need to be performed, as we talked earlier, and traffic goes out. This is when there is no congestion on a VOQ or on a port. When these VOQs or port are under congestion, then these VOQs are migrated to HBM. We'll talk in detail about that, but what happens is those VOQs are migrated there. Now, what's the reason? One, SMS has a very limited size, right? It's about 36 megabyte, if I'm not mistaken. HBM is 8 gig, a lot of space compared to SMS. So once you have congestion, it means that you need more VOQs, and then those VOQs got migrated to HBM. So this is the diagram here. So as we can see, HBM, why we call it the external memory. If you see, this is the ASIC die. Within the ASIC die, you have the on-die buffer, VOQ, which is your SMS, and then you have HBM. Now, in case of congestion, actually, we do use HBM. And what else we can use for? If we fib expansion or some of the other reasons, but main reason is if your port or your VOQ is under congestion, VOQ is migrated to HBM. So SMS is your primary VOQ packet storage memory, and then HBM is the secondary. When a VOQ in SMS is getting over congested, it just got evicted to the HBM, and when evicted, VOQ becomes empty, means that HBM has those VOQs, traffic has drained out, it migrated back, or it goes back to the SMS. This is one of the commands, show controller NPU slice info. It gives you some of the information about the HBM, just showing this command in case if somebody wants to look at the HBM information. So HBM is XDI, what is the NPU version, and so on and so forth. This is not kind of regular troubleshooting command, but rather here we are trying to pull up some information about the status of the NPU and the HBM. There is a command actually coming up which will show you that which memory we are using. So let's take the example here. We have a Spitfire right here, R1, R3, and then R2 is Spitfire. Incoming port is P0, and then we have a P1 egress interface. When the packet comes in, and we have a traffic class 0, VOQ offset. So let's talk about VOQ offset real quickly. So in a certain commands, actually, when you see the VOQ ID, it will give you the VOQ base ID. What it means that it will give you the VOQ 0 ID. That's, we took the example of 1000 in the beginning, right? So VOQ offset is 0 to 7, and your VOQ ID, let me go through this. Right. So your VOQ ID is your VOQ base ID plus VOQ offset. So for your VOQ 0, your offset is 0. Your VOQ 1, your offset is 1, and VOQ 7, offset 7. Your base ID will be shown with that command. We'll look into that in a few minutes. But your actual VOQ ID will be addition of base plus the VOQ offset. So offset will be 0 to 7 for all the VOQs. Now your packet comes in. The route lookup happens in RxPP, and then this is ICS ingress credit scheduler. It requests the credit. Credits are granted. This is regular stuff we talked about earlier, and then the packet transmission happens. ACL or remarking or re-encapping happens on the TXPP side, as we mentioned earlier. So this is a flow here. The last line, if you see that RxPP, it does the marking. If there's a marking needs to be done, so marks the traffic to the traffic class 0. Lookup happens, VOQ lookup happens, and selected the VOQ based on your marking and classification and marking. And then the ingress is credit schedule comes into picture, request the credit is granted, packets are switched to the output queue, and the TX scheduler comes into picture, sends the traffic to the packet processor, and then marking or remarking ACL happening on the egress side and packets are put on the wire. So that's at a high level, the packet flow within the system. Now, this is one of the commands when there is no congestion, only SMS is being used. Slice VOQ is SMS. This is when there is no congestion. So let's look a couple of more things while we are on this topic actually. So show controller NPU VOQ usage interface command. So what it gives you, this is your egress interface. So keep in mind in this command, like I mentioned earlier, certain command has 2 variables. So this is that command where we have 2 variables. This is kind of fixed system, I believe, where you are looking at the RP0, but this is your egress interface. So keep in mind when you are looking at the VOQ, you are looking from the egress interface perspective. You are looking at the VOQ from the egress interface perspective. So when you are running this command, this is your egress interface and this is your incoming line card. In our case, it's a fixed platform. So what is your VOQ base? This is a VOQ base I was talking about, which we took the example 1,000 until now, but it's 16,510, right? So now you have an offset 0, which is this is your VOQ 0. Then you have offset 1. So VOQ 1 will be 16,513 and so on. And next will start 16,519. Next means the next set of the VOQs will start. Another important thing is the local. Local, and in some commands you will see the remote as well. So it means that this egress interface with respect to the incoming or ingress line card is local versus remote. So if you have 00034 and let's say you have 01 CPU 0, it will be remote compared to that ingress line card. So you will see the keyword remote. So while we are on this, we just understood that what is the VOQ base here and what is the port type local. But this command is showing that what memory is being used. And once you have congestion, you will be using seeing the HBMO here. And keep in mind, again, this question I was expecting will come later on probably. Your default queue limit is 6 milliseconds. And we can do some calculation later on in some of the commands, but the default queue limit is 6 milliseconds. So HBM block, how much time we have? So let's try to cover this HBM block section, and then we probably will continue next time. I think we are pretty much running out of time. So HBM block is, H block is 8 kilobyte in size, total 1 million blocks, so 8 gig of memory. Typically, we use 6 kilobytes for the packet storage, so that's about 75% of the usage. And a maximum we can have 32 packets can be stored in one block. So if we have a large packet, which is greater than 8 kilobytes, we'll use multiple HBM blocks. Just like if you compare this with the packet converted into cells in the fabric, so one packet can take multiple cells. So for a smaller packet size, let's say we have a 100 byte packet size, because of the maximum 32 packets per HBM limitation, about 45% of the HBM block will be used for the packet storage. So you have a smaller packet size, your usage of the HBM will go down. But again, this won't impact our discussion later on. We'll revisit some of these points once we run some of the show commands. So let's see how we do the congestion management. We'll start this topic, probably will not be able to finish this one, but we'll see that how much we can cover today in next 5 to 10 minutes, and then we'll continue that hopefully next week. So a couple of things, and these are the important things, right? So NPU drop points. Why it is shown here, your PPS drop is before VOQ. So if there is a PPS drop, it has nothing to do with the VOQ, that's one. And then if you have a route lookup drop, for example, there might be a command here in next few slides, which will show the route lookup drop. That again has nothing to do with the VOQ. Your unicast port congestion drop happens, that is on the VOQ. Your multicast port congestion is again not on the VOQ side, but rather it's on the TXPP or at some other level as well. The multicast traffic is not scheduled. So a couple of things, PPS drop and the route lookup drop, not in the VOQ. It's before VOQ. And if you have a congestion drop, and we'll see again some of the commands that where we can see these drops, that is related to the VOQ. At a high level, I think we can pretty much skip through this slide. Packet comes in. If it is the egress interface is on the same NPU, you don't have to go through the fabric. If the egress interface is on a different slice or different NPU, different line card, it has to go through the fabric. I think that's a packet flow, high-level packet flow. We have gone through that one. This will give you a little more detail about what happens there.
Just a quick question here. On the previous slide, when packet goes in and out on the same line card, it skips the fabric, but does it still go through the whole VOQ credit request edit available kind of message?
Yes. Yes, yes, that's true. Because
so
credit request credit scheduler has nothing to do with the fabric. Yeah, that's right.
Got it. Thank you.
So we have a receive buffer. The receive buffer is carved into per interface queue, and packet data from the wire is stored in the receive buffer once the packet is received, and then it's sent to the packet processor on the receive side. So receive interface schedules packet from per interface queue to the receive buffer and send to the RxPP in proportion to the speed, the interface speed. So if we 10 gig versus 100 gig. So on the RxPP execute, what happens? We talked about that ingress QoS feature like the classification, marking, and policing. It happens on the RxPP. Since the NPU architecture is a single stage forwarding, here we decide that what is our final destination, means that final destination for the line card and what slice and what interface. So that is determined at this level. Then the packet is written into the internal memory, which is SMS, and a packet descriptor is generated here. And that packet descriptor is included in the VOQ corresponding to that particular destination front port, means that what is the egress interface. Then credit request, credit grant, then the packet starts forwarding, again based on what is the egress interface. So this is again, this probably has nothing to do with the QoS feature itself, so I'll try to skip through this one, but this is your regular packet forwarding on the Spitfire platform. Where your fabric load balancer actually comes into picture and selects the least least congested fabric link, and then which provide the connectivity to the egress NPU, and then it sends it across the fabric, goes to the particular FE, depending upon which fabric we are using. It goes to the egress NPU RX buffer. From the RX buffer, it goes to the RxPP, and then goes out on the wire. So regular packet flow. So now packet flow under congestion. We'll stop over here. But earlier we talked about when there is no congestion, packet goes to the SMS. But in case of congestion, actually, these VOQs are migrated to the HBM, and we have 8 gig. The speed between the HBM and SMS is 1.8 terabit per second, and that's more than enough to actually handle any incoming traffic. So that will not be a bottleneck. If somebody might be asking that, what's the speed between that, and might be there is a drop between that. No, there won't be. So again, in this case, once you have the congestion, actually, your queues are migrated, then your credit request and credit grant happens to the HBM. So earlier, when there is no congestion, no buffering, actually, credit request, credit grant on the SMS side, and then once you have the congestion built up, queues are migrated, and then credit request, credit grant, same process happens, but through the HBM. These are the packets being transmitted. So this command, let's take this as a last slide. Let's just talk about that. Show controller NPU debug and NPU number. These are the scripts actually. There are multiple scripts, and these are the commands. Probably there is a side project might be ongoing to convert these into the XR. Have to check back if that is still the case. But for now, actually, these will be the cheat sheet commands actually we all have to deal with for now. But what's shown here is different drops. As we can see that this is the interface RX 0 full drop. This is your PPS drop. It has nothing to do with the QoS. So when you see that PD VOQ drop here, before this line, any drop is not related to QoS. So this is your PD VOQ, because your before your VOQ, what happens? Your marking and your policing and your classification. But once the packets are in the VOQ, actually, and if there is any drop, you will see that those drops here. So the script is print get counter based on the location, and it will give you all these counters. But for now, we are focused on the PD VOQ drop, and that will tell you that there is a drop in the VOQ. Now, this will only tell you a drop on slice 0, right? Now, within slice 0, you have 8 VOQs. Now, which VOQ is dropping the packet? We have to use certain other commands actually to go into that detail, and we'll talk about that in the next session. So, Akhilesh, how you want to take it forward? Actually, I think we are out of time.
Yes, yes, we are. We are on time now, a little bit above than that. So maybe the remaining part we can schedule for the next session next week. How about that?
Yeah, we'll do that. If you can stop the recording, a couple of things I can quickly address that if you have to.
Mohammed, I have one question on the congestion point of view. Can you go to the slide 37?
37,
so here,